right. Well, should we? Let's start on time. So we're very happy to have Liam Fitzpatrick from Stanford University. Liam is a theorist who's worked on pretty much everything that it's possible to work on as a theorist. He's worked on particle physics, cosmology, condensed matter, and now he's currently working on the Conformal Bootstrap, and that's what he's going to tell us about today. So, Liam.
Great. Thanks very much for the introduction, for having me here. As Marcus mentioned, I work on a variety of things, and what ties these all together in my mind are my two passions, which are effective field theory and conformal field theory. Okay, I like these tools because they're very powerful and versatile, can be applied to a wide range of subjects. Okay, last time I was here, I gave a talk about some stuff I've done with effective field theory, but today I'm going to tell you about work I've done on conformal field theories, and in particular applying the conformal bootstrap equation to learn about universal dynamics of conformal field theories. Okay. So I'll get into some of what that means. Right, first I want to start off with some basics, all right, and quite a bit of motivation. And so first of all, what are conformal field theories? Okay, they're quantum field theories that have conformal symmetry. Okay. And conformal symmetry is very easy to state. Okay, conformal transformations are just coordinate transformations that preserve angles in special relativity. Okay. So simple example are rotations. If you take two vectors and you rotate them, the angle doesn't change. More interesting example are scale transformations. If you take the same two vectors, you scale down their magnitude, again the angle doesn't change. And theories that are invariant under scale transformations have very interesting properties. Right? You look at them in one scale and you zoom in, you see the same thing. So if you see fleas in your theory, they have to have fleas on their backs, and there have to be fleas on the backs of those fleas, and so on forever. Okay? What? Yeah. Ad infinitum. Yeah. Fleas on their backs to bite them. And so on ad infinitum. So, why are CFTs interesting to study? Why do we spend our time working on them? And some of you may be thinking, okay, I believe there's some beautiful mathematics here, but as physicists, we also like things that we can really put our hands on.
I like the tie.
So, do these connect to physics that we can really hold on to? And the answer is emphatically yes. Okay, CFTs are central objects in physics. Right? They connect to a vast range of interesting physical phenomena. Right? I've listed a couple examples here, which I'll say more about each of them, as well as a few other ones. Okay, I don't have time to discuss all of the connections that I think are most important. Okay. I think almost no matter where you come from in physics, there's something for you in the study of CFTs. And over the last 40 years or so, they've really emerged as one of the most important objects of study in theoretical physics. So let me start with some of these connections. The first one I want to discuss is possibly the most down-to-earth, the theory of phases of matter, right? Specifically transitions between those phases. So here's a picture of the phase diagram of helium-4, right? Temperature on the x-axis, pressure on the y-axis. There are a number of different phases and transitions between them. And the places that are relevant for conformal field theories are so-called critical points, critical phase transitions. Right? These are places where the correlation length of the theory diverges, and there's no longer any intrinsic length scale in the theory. Okay? These are much harder to study by traditional means. The infinite correlation length means essentially an infinite number of degrees of freedom are all correlated with each other. Fortunately, the conformal invariance of these theories gives us a powerful tool to study them. Okay? So what are the kind of things we're interested in? Right? One of the main things are critical exponents, or scaling dimensions. These control things like how the specific heat scales as a function of temperature. Okay? And these are things we can concretely measure. Okay? So here are a number of critical points. Right? And in each of these cases, we have a concrete CFT, right, that we can use to make precise predictions about these scaling dimensions. Right? And you can see there's a fairly impressive agreement between theory and experiment. I want to mention, in this case, this number here for the liquid gas, actually the most precise calculation on the theory side comes from the type of bootstrap methods I'm going to discuss today. We can also go back further in our education to the very first field theory we ever learned about back in kindergarten, namely classical electromagnetism. Turns out Maxwell's equations are conformally invariant, although he didn't know it at the time. Right? And sort of a simple, rough way of summarizing this is that if you know how the photon behaves in the vacuum at one wavelength, you know how it behaves in the vacuum at all wavelengths. Okay? Now, this is no longer true beyond the classical level. Once you turn on quantum effects, okay, the theory does change with scale, but it changes very slowly. So it's approximately scale invariant. Okay? So scale invariance is still an approximate symmetry of the system. And this is part of a more general theme, which is, yes?
So for E&M,
yes,
without matter,
right,
then quantum doesn't change its conformality. I just want to make sure.
Yes, that's true. So the if you add, yeah, it's if you add in it's when you add in matter that quantum corrections. Yeah, that's right.
Thank you.
Or if you go to third grade, you can do non-abelian gauge theory.
Or you could do non-abelian gauge theory if you go to third grade.
Okay, is that okay? This is a more serious question. For Young-Mills without matter, just Young-Mills itself,
Yes.
quantum when it becomes quantum field theory,
Yeah.
is conformality known or not?
It is broken. Conformal symmetry is broken at the quantum level in non-abelian gauge theories in Yang-Mills.
The usual Young-Mills,
Yeah.
no super, no nothing.
That's right.
Great, thank you.
Okay, but it's broken by a small amount. All right, and this is part of a more general theme, which is the vast majority of quantum field theories we study, okay, are approximately scale invariant over wide regimes in energy. Okay, so they change as you zoom in, but they change very slowly. And the way we think about this is renormalization group flow. Okay, the couplings change as you change scale. Right, the most famous example of this is grand unification. Right, the strength of forces at energies we see them are different. Right, in the standard model, as you go up in energies, they change and they all come together. But in some ways, the most impressive thing is how little they change. Right, this plot is over about 6 orders of magnitude in energy, and the couplings are changing by fairly small amounts. Okay, so quantum field theories tend to be approximately scale invariant over wide regimes. There are few boundaries over which the description of the theory changes quite suddenly. Okay, and there's a large distance between these boundaries. And this ability to think about things as being close to scale invariant theories is not just useful at weak coupling, but it's useful at strong coupling as well. And in fact, strongly coupled physics is where conformal field theory, where conformal invariance becomes most powerful. Okay? Because it's that strong coupling that most of our methods, which are based on perturbative expansion and the coupling, these methods break down. When theories are conformal, just the conformal invariance itself gives us a powerful tool, which often allows us to say concrete things. Okay. One of the most remarkable tools that comes out of this is we can describe many strongly coupled 4D theories, which are approximately scale invariant, by looking at 5-dimensional theories, okay, which turns out to describe them, where the 5-dimensional theories are weakly coupled, the geometry is curved, they're what are called warped extra dimensions, or Randall-Sundrum models. Okay, and here, since the theory is a weak coupling, we can write down concrete models, we can try and address specific problems, okay? We can make very precise predictions. And this allows us to explore classes of strongly coupled 4D physics. Right? And this is where I personally got into this question of conformal field theory, right? Was by studying Randall-Sundrum models. And I wanted to understand, how wide a class of strongly coupled 4D physics was this allowing us to explore. Okay? When we look at 5D models, we make some assumptions. Okay? For instance, we assume they're local, they can be described by a Lagrangian. Okay? are these restricting us to a tiny regime of all possible strongly coupled models, or are these assumptions sort of generic in some sense? And this is going to be a major theme of this talk. What types of things, coming from the four-dimensional point of view, are generic about the five-dimensional theories? Okay? What types of things are universal? This connection between 4D and 5D theories is part of something much bigger, what's called the ADS-CFT correspondence, which is one of the most profound discoveries in theoretical physics in the last few decades. What it says is that conformal field theories in d dimensions are in fact equivalent to theories of quantum gravity in anti-de Sitter space in d plus 1 dimensions. Okay. What makes this so powerful is there's still a lot about quantum gravity which is mysterious to us, okay, which we don't know. There's much less which is mysterious to us about conformal field theories. Okay. We believe we know in principle how to define them. Okay. And by studying this side, which we know much more about, in principle, we can answer any question about quantum gravity in ADS. So these two things are equivalent to each other, right? Studying one tells you about the other. So if you spent your whole life thinking you just cared about gauge theories in 4 dimensions, you didn't care about quantum gravity, turns out you were wrong. Secretly, all along, you cared about quantum gravity. Right? And vice versa. Studying conformal field theories can tell us about quantum gravity. Okay, yes?
Again, a clarification. The conformal field theory always involves super something, right?
Does not.
Does not?
Does not.
Okay, that's good to know. Okay. Ordinary. No super.
Supersymmetry is not a necessary ingredient of this.
Thank you.
All right. So what types of questions would we like to know? Okay, about? One of them just gets to the heart of why is this equivalence true at all? Okay, why is this extra dimension, which emerges from a CFT, what you can think of as a true geometric extra dimension? Okay. In some sense, you can think of any coordinate as a dimension, like the color of an object, but that's not really what we mean by an extra dimension. Right? We mean there's some sense of locality, that as things become far apart in this coordinate, they stop interacting with each other. Okay? So why is that true? A second thing we'd like to understand is why do gravitational interactions emerge? More precisely, I mean what kind of gravitational interactions? Are they familiar theories, things like Newtonian gravity and general relativity? Or are they weird, modified theories of gravity, okay, things which are more unfamiliar to us? Another thing we'd like to know more about is dynamics about black holes. Okay, this is really one of the essential parts of what makes quantum gravity hard. Okay, is at the semi-classical limit, as Hawking showed us, black holes radiate. Okay, they have an effective temperature. Okay, and they create a thermal background, and this thermal background contains no information. Okay, so if you have something incriminating written in your diary, and you want to dispose of it, the semi-classical level, you can throw that into a black hole, right? Black hole will eventually evaporate to radiation, and all that information is lost. Okay. This is not consistent with quantum mechanics, which says information is never lost, right? The wave function evolves in a unitary way. So one thing we'd like to understand is how is it that something that looks semi-classically like a thermal background can actually be a pure state, okay? And understand this description better. So here are the goals of this talk. Right? First, I'm going to use the conformal bootstrap equation to learn things about universal properties of CFTs. Okay. The second goal is I'm then going to take those results about CFTs and interpret them in the context of this equivalence as statements about gravity, right, in the extra dimensions. Specifically, I want to derive locality in the higher dimensional theory and properties of gravitation at long distances. However, I want to emphasize I'm not going to assume anything a priori about the dual gravitational theory. Okay, at some level, I'm not going to even assume it exists. I will certainly not assume it has Lagrangian. I will not assume that it's general relativity. Okay? If you want, if quantum gravity isn't your thing, right, you can watch this whole talk as just a talk about conformal field theories, and everything will still go through. Okay? think that would be a mistake. I think a lot of things that we learn are become more intuitive when we think about them in terms of ADS. Okay. But you don't have to. So this is the road we're going to go on. We'll start with the bootstrap equation, which I'll describe to you. We're going to learn things about strongly coupled physics, okay, of conformal theories. This will teach us things about extra-dimensional rules. Yes?
You say it's an equation, so there's no equal sign. Can you elaborate?
Yeah, this arrow is time, and this is the path that I will take you on in the next 45 minutes.
Okay.
Okay. So you will be a different person 45 minutes from now, but you will have gotten there in a unitary way.
Hopefully I'm not in the black hole.
All right. So the things we'll see are locality, right? Why, when you take objects far apart in this extra dimension, it becomes hard for them to hear each other. Learn about the presence of a Newtonian gravitational force, an inverse square law force, in its generalization to higher dimensions. We'll see this emerges universally at long distances. And then the last part of the talk, I'm going to focus on 2D CFTs. Here we're going to see that heavy states in the CFT effectively deform the CFT geometry. Okay? This is fairly remarkable because this is in a theory without gravity, without making any reference to the gravitational theory. Okay? Right? The gravitational theories can just be whatever weird thing is consistent with the constraints of conformal field theory. Major tool that gets us there is the conformal bootstrap, which sort of graphically is this equation, which I'll now describe.
Good, that's what I was in mind.
What is the conformal bootstrap? Yeah. All right, so first let me introduce some important notions about the study of conformal field theory. All right, in conformal field theories, one of the key roles is played by operators. Okay, this is just another word for a local observable, okay, in quantum mechanics. All right, this can be something simple, like the local density. Okay. What we are mainly interested in studying are correlation functions among these operators. Okay? And this is really what you would just naively guess it is. It's you take the product of this operator of 3 points and you take the average, right? So you could imagine, in principle, preparing the vacuum, measuring the density at 3 points, writing those numbers, preparing the vacuum again, measuring them again. Okay? Then the end, you just multiply the 3 numbers and take the average. So it's really just an average. All right. That's what we mean by this correlation function. Most of the things we're interested in can be extracted from knowledge of the correlation functions. Another important point is that in conformal field theories, we can associate operators with states and vice versa. Okay? So you can think of this as any operator you have, you can create a state, just take that operator and act on the vacuum. You can think of this as by measuring this observable, you perturb the vacuum and put it in a state. Yes?
Could you just be a little bit more specific? What do you mean by a vacuum? That is, what is the operator which annihilates that becomes zero? The operator which to this vacuum equal to zero.
This, I mean, by the vacuum, I mean the ground state of the theory, so the zero energy state of the theory.
I see. Thank you. So you do have a Hamiltonian.
Yeah, so actually, maybe this is something I should spell out more. I'm going to be thinking, so there's a Hamiltonian, yes, and that's actually, the Hamiltonian is part of the conformal algebra. Okay, it's actually one of the symmetry,
The
time translation is one of the symmetries.
L0?
In 2-dimension CFTs, it is so-called L0 plus L0 bar. That's right.
Okay.
Well, that's the dimension, okay, of the theory.
So here's the question. I thought the spirit of bootstrap is you don't have Lagrangian or Hamiltonian. So therefore you use the conformal algebra. So you say the generator. So the L0 is in your conformal spirit.
We don't have a local Lagrangian or a local Hamiltonian. However, we do have conformal symmetry of the theory.
Right.
And okay. So we have an operator which generates the symmetries.
Good. Okay. So you use your conformal algebra. That's better, consistent. You don't need to have the Hamiltonian.
We don't have a local Hamiltonian. That's right. We don't need one. Okay. This allows us to study theories which may, for all we know, have no local Lagrangian description.
Okay.
All right, so one thing that's useful about conformal field theories is this mapping from operators to states is one-to-one. So there's a unique state associated with operators. Okay, so I'll use this. I'll go back and forth between these two, right, referring to operators as states and vice versa. Okay, and I'm using this connection. Now we can look at more complicated things where we have several operators. Okay, the simplest such thing is the insertion of two operators, right, which I've denoted as two ripples in a pond here. And one way of simplifying this, which is common in problems in physics, is to decompose it into a convenient basis at some fixed radius. Okay? Right, so common basis is spherical harmonics. Since this is quantum mechanics, what we're doing here is we're decomposing the wave function. Okay? So this is the basic intuition that underlies what's called the operator product expansion. Right? This was first taught to us by Ken Wilson in the late 60s. What it says is if you take any two operators and you multiply them, you can decompose that product, okay, in some basis of operators. It can be whatever basis you like, as long as it's complete. And the coefficients in this decomposition are just functions. These are called OPE coefficients. Okay. This operator product expansion is very powerful when it's used inside correlation functions. Okay, so, for instance, we can talk about a 4-point function, and I can apply this operator product twice to these two guys, and you can see I've reduced it to a sum over 2-point functions. You can convince yourself that the OP coefficients are themselves just 3-point functions. One thing that's special about conformal field theories is the sum converges. Okay, it has finite radius of convergence. So that means this 4-point function is completely determined by the 2 and 3-point functions of the theory. In fact, all correlation functions are determined by 2 and 3-point functions of the theory. Conformal symmetry gets us even more than this. It allows us to group many of these terms together, constrain the form of others. Once all the dust settles...
In general, do field theories always satisfy this condition, or only conformal field theories?
So in general, the operator product expansion does not have to converge. Okay, it does not have to have finite radius of convergence. It's only in conformal field theories that it has to.
It always exists.
The operator product expansion, you can always do the operator product expansion. So, right, good. So, conformal symmetry allows us to massage this into a much simpler form, which is unknown numbers, okay, these are just numbers, times known functions. Okay. These functions are conformal blocks. They just depend on the dimension and the angular momentum of the operator. Okay. And they're basic building blocks, okay, in the conformal bootstrap. A lot of work goes into calculating these functions. Okay, so now I'm ready to present the conformal bootstrap equation to you. It's just the following observation. So in the previous slide, I took the operator product of this pair and this pair. All right. It's clear there was nothing special about that choice. Right? It just as easily have taken the middle pair and the outer pair and get a different decomposition. The conformal bootstrap equation is the deceptively simple statement that these two decompositions have to give the same answer. Right? We've taken the same 4-point function, we've decomposed it in two different ways. Okay? So these two pictures, these two different decompositions. This simple statement turns out to contain an enormous amount of physics. Right? I'm going to show you how to extract a lot of this physics. I'm going to use this equation together with an important general fact, right, which is that if you look at fluctuations on short distances, they diverge as you zoom in to shorter and shorter distances. Okay? So you can think of this as just the variance between two operators as you bring them close together, okay, as a singularity. The strength of this singularity is completely determined by the scaling dimensions of these operators. Okay? More or less just by dimensional analysis, you can see this has to scale in a certain way. Okay. And the presence of this singularity tells us several important things. Okay. It also shows up not just in the 2-point function, it shows up in 4-point functions. So we can imagine taking the 4-point function of two densities and two currents. Okay? Right? And we have a contribution from the diverging variance, when we bring the density together and the two currents together. Okay. So we have the singularity from this guy and the singularity from this guy. All right. These singularities must be reproduced by the sums in the bootstrap equation. Okay. And the fact that they must reproduce these singularities tells us a lot. Rather than go through the details of the proof, I want to go through a very closely related analogy, which I believe will be more familiar to many of you, okay, which is the spherical harmonic decomposition of Coulomb scattering. Okay? If you look at Coulomb scattering, just two charged particles scattering with a photon, you have 1 over q squared, where q squared is the momentum of the photon. You can work out is 1 minus cos theta. So there's actually a singularity in the limit of forward scattering. Now you can take this scattering amplitude and you can decompose it in spherical harmonics. And the important point is that spherical harmonics are just polynomials in cosine of theta. Right? So they're all regular as cos theta goes to 1. Okay? So the only way the singularity on the left-hand side can be reproduced is by an infinite sum over spherical harmonics with large angular momentum on the right-hand side. In fact, there's a theorem in real analysis called the Hardy-Littlewood theorem, which says if you know this singularity on the left-hand side, then you immediately know the asymptotic value of these ALMs in the limit of large angular momentum. Okay? We're basically going to do exactly the same type of analysis in the bootstrap equation. Right? We have a singularity that has to be reproduced. Right? We have sum over operators with large angular momentum or large spin. This is going to allow us to prove the existence of certain large spin operators in conformal field theories. It'll let us determine their scaling dimensions and their OPE coefficients. Right? This will in turn demonstrate certain universal properties of the long-distance physics in anti-de Sitter space. Now we want to go on a bit of a digression to explain this connection. Why is it that large angular momentum in the CFT corresponds to long distances in ADS? This brings me to what I like to call ADS-CFT kinematics. Okay, these are things that follow purely from the symmetries of the theory. Right? They don't depend on the dynamics at all. Alright, so I've mentioned anti-de Sitter space several times. Now I'm going to give a very brief introduction to it. My favorite way of thinking of ADS is as a very special box. Okay? It has lots of properties we like. Here's one form of its metric. Okay? And here I've drawn a picture of this box for you. This box is not drawn to scale. There's actually an infinite amount of volume inside this box. It has constant radius of curvature. Okay? And I'm always going to be working in units where this radius of curvature is 1. Okay? Perhaps the most important thing about this box is that it's maximally symmetric, and its isometries are an exact 1-to-1 correspondence with the generators of the conformal. Okay. This immediately tells us several things. First thing it tells us is that energy in ADS corresponds to scaling dimension in the CFT. That's because the Hamiltonian, which generates time translations, maps onto the dilatation operator, which generates scaling. So you could take a state in ADS, you evolve it from a young state to an old state. It's the same thing as in the CFT, using the dilatation operator to evolve a skinny state to a not so skinny state. So it's not too soon to poke some fun of the Kennedys. You should know, I personally am allowed to make fun of the Kennedys since I'm half liberal. I also like this example because it's a great example of duality, right? So time translation on Kennedy states is the same as rescaling of Kennedy states. All right, so this one-to-one mapping between the symmetries tells us this, but also gives us much richer information. Right? States in the CFT have wave functions in ADS, okay, which are completely determined by symmetry. All right? Start with a simple example. Primary states, these are basically states created by operators which are not the derivative of any other operator. Okay? You can work out their wave function, and this is what it looks like. They're very boring, right? They just sit in the center of ADS, don't do anything. get something more interesting, you can get states created by operators where we take a few derivatives. Now these have wave functions which sort of oscillate back and forth around the center of ADS. Okay. And in fact, it's technically very accurate to think of ADS as having a geometry that creates a potential well, okay, which pushes objects towards the center. So what we've basically done by taking a few derivatives is we've gone in, we kicked the state, right? Now it just oscillates back and forth, right, at the bottom of this well. Yes?
Can you just say a little bit more about what the definition of that wave function is?
Yeah. What I mean is, take the following,
Other way around.
all right, and then here is the state we're looking at. Okay? Now I'm going to demand that this transforms like a scalar. Okay?
So that's some scalar
Yeah.
and some
Yeah.
other operator.
This is a descendant operator. Let me start with the primary. Okay? The simpler case. Now, because this is primary, that means it's annihilated by the special conformal generators. Okay? You can think of special conformal generators as lowering operators and derivatives as raising operators. All right. So that kills this, but that gives you a differential equation that is satisfied by this.
So that's the phi is the field in the ADS that corresponds to that operator.
That's correct. Yeah. All right. And it's completely determined by the fact that you know how the generators of the conformal group act on it.
So
Are
you
you
go
saying all
from-
the primary operators are equal to
I'm saying any primary operator. Okay. Here, for simplicity, I'm talking about a scalar primary operator. Okay. Here, this is a function of coordinates in ADS. Okay. You know the action on this operator of the generators of the conformal algebra. That's a differential equation that has to be satisfied by this function in ADS. It allows you to solve for what this is. Is that clear?
Yeah, just notation. Is this phi what's psi on your screen?
Yes, sorry. So phi is equal to this whole thing.
Oh,
Phi is equal to this
Okay.
prefactor times.
Thank you.
Okay. All right. Great. Thanks for asking. All right. So now we can get something much more interesting. We can take derivatives, take a whole bunch of them, don't contract their indices. So now we get a large spin, a large angular momentum. And now these guys have wave functions where, because we've given this huge angular momentum, this gives them a centripetal force which pushes them up the potential well. The more angular momentum they have, the farther up they go. And the farther they go from the center of ADS. Okay? You can look at the detailed form of the wave function, just read off that the radius they go up to is given basically by their angular momentum. For those of you who are experts, by radius here, defining the radius in terms of the area of the sphere. Okay? That distance. All right. Now we want to talk about locality. Okay? And these wave functions, right, they had coordinates, but so far they were just labels. Okay? Nothing that I said so far says that these really are geometric in the sense that objects which are far apart in these coordinates stop talking to each other. So we want some sense of locality, what's sometimes called cluster decomposition. Now I want to sharpen this criteria. Right? To do this, I'm going to introduce a state, which I'll call rock. And to compare it to something, I'll introduce another state, which I'll call scissors. And our question is, can these two coexist peacefully? That is, does the CFT have what you might think of as rock plus scissors states where they're far apart and ignore each other? Okay? Or do they necessarily always get together and try and duke it out? Okay. And we know how this story ends if they get together. Doesn't end well for scissors.
So locality is not precisely cluster decomposition. Cluster decomposition is better to say that this is asymptotic commutativity, because string theory is considered to be non-local, but cluster decomposition still is there.
So I'm going to give you a definition by what I mean, okay? And you're free to like this definition or not, okay? But this is what I am going to call cluster decomposition, okay? And I'm going to define it sharply in terms of the CFT, all right? So in order to make a definition, first I want to have some notion of how do you take states which are far apart in ADS. I want to define this purely in terms of CFT. Okay? We've already talked about how to do this. All right, we can give them a large angular momentum, right? So they orbit the center at large distance. So I'm going to formulate this criterion in terms of states in the CFT with large angular momentum. Okay. All right, and here's what I'm calling cluster decomposition. Okay. My definition is that if you hand me any two primary operators in the CFT, I'll call them phi rock and phi scissors, okay, then there exists an infinite number of operators at large angular momentum. These operators have dimension, in their operator product expansion, and these have dimension which you can think of as a free part. This just depends on the dimension of rock and the dimension of scissors. Then you can have, there's an interaction part which depends on the specific theory. And the theorem is that as angular momentum goes to infinity, this interaction part goes to zero. Okay? So you just get this universal term. All right? This turns out to be true in all CFTs in 3 or more dimensions. Okay? And the proof basically follows, right, from the type of argument we discussed earlier. You know that there are these singularities from the variance, okay, and that has to be produced by the bootstrap. What's special about 3 dimensions or higher is you can show that that variance is the strongest singularity that can contribute. Okay? There can't be any other. It strictly dominates over any other singularities, though. Okay? It's not true in 2 dimensions, okay, which we'll come to later. And this is a universal feature of all CFTs in 3 or more dimensions. However, there's more information contained in here if we look in the limit where angular momentum is finite, but just very large. Okay? The reason is that you can think of this sort of correction term to the dimension in the CFT as a correction term to the energy in ADS. Right? So this is like a binding energy between these distant guys. Okay? Furthermore, because angular momentum corresponds to distance, this gives us a simple handle on how this binding energy depends as a function of the distance between them. Yes?
Is that delta naught, is it just the sum of the dimensions of the 2 operators?
Yeah, so that's exactly right. So I've simplified it a little bit because, okay, but delta naught, there's actually another parameter that I've suppressed, which is an integer parameter. It's equal to delta scissors plus delta rock plus 2n plus L. Okay. There's actually, so I haven't.
N is the number of the you've got some descendants.
You can think of n as, you've taken something like this. All right, so I've suppressed it for simplicity, but actually there's not just one of these guys. There's actually an infinite number of towers, right, at large spin, and they all are present, and they all have this property. All right, so good. So by looking at how this correction term depends on angular momentum, we learn about how the binding energy between these 2 guys depends on the distance between them. Now, so far I've talked about this singularity that comes from the variance in 2 objects, but there are other universal singularities that are also present. Okay? One of these comes from the fact that if you look at the operator product expansion of an operator with itself, the energy momentum tensor is also there. That corresponds to another singularity, which you also know everything about and is universal. The strength of the singularity comes from the dimension of the stress tensor, okay, which is fixed to be d in d dimensions. You know the coefficient, you know the operator product coefficient, it's completely fixed by conformal invariance. Okay? And what you learn when you demand that you reproduce the singularity is that there has to be a subleading singularity, which is matched by a correction term of the following form, okay, which is exactly of the form of a Newtonian binding energy. To write it in this form, I've translated CFT quantities into ADS quantities. So m rock shows up as the dimension of rock, because energies and dimensions are related to each other. The radius shows up as the angular momentum. Okay? And G Newton shows up as something that is essentially 1 over the number of degrees of freedom. Okay? More precisely, it's 1 over the central charge. So in order to see that this is present, you need to be able to say that this singularity also strictly dominates over other things. And in order to make that happen, you need one fairly mild assumption, which is that the CFT has to have some interaction. It can be very small, okay, but it has to be some non-zero interaction with CFT. And once that's true, then you find that this is universally present. Okay.
And rock is somewhat, the actual formula is quadratic in delta. Is delta minus this. Is that guy, right?
Yeah. So the actual formula is, so there's some factor that has to do with the normalization of wave functions. Okay. But you get some universal formula, okay, which matches what you get from the calculation in ADS at long distances with Newtonian gravity. And for those of you who are experts, I want to emphasize I haven't made any large n assumption. Okay. N here can be anything, it could be 1. Okay.
No supersymmetry.
I've made no assumption about supersymmetry. Okay. I've made no assumption about perturbativity. All I've assumed is that the theory is unitary, it's in 3 or more dimensions, okay, and it's not a completely free theory.
And
Okay.
G Newton is dimensionless just because you're taking the ADS radius.
Exactly.
Yeah.
Exactly.
Okay.
All right.
But in this assumption, do you have any proof that you have correspondence with ADS and CFT, which includes locality? That's the main question.
Well, so I've proven the things that I've proven these things as statements about CFTs, okay, and you're free to interpret them as statements about ADS. So I'm arguing that we have basically proved locality, okay, at very long distances. Okay. Yeah. Now you can define. There are different ways to define locality. This is one definition. All right. So now I'm going to switch gears and talk about 2D CFTs. Okay. Let me say a few words about why I think it's a fruitful idea to focus on 2D. Okay. I think they're useful as a toy model. Okay. For one, conformal symmetry is much bigger in 2 dimensions. Okay. The conformal group is actually infinitely large in 2 dimensions. Okay. Gravity in 3 dimensions is also much simpler. The gravitons have no degrees of freedom. Okay. However, there are still black holes in ADS3. So this has the kind of flavor of what we'd like from a toy model. Simple enough, we can hope to make progress. Rich enough, we believe it has the physics that we're mainly interested in. Right? Toy models have played, an important role in many areas. So some other 2D models are the Ising model. The Onsager solution taught us a lot of phase transitions.
When you say 3D, it is 3D that is with the same sign of the method, not mean also 2 plus 1.
I haven't really talked about this point, but in what I'm doing, it's important that I'm basically using Lorentzian signature. Okay.
Oh, Lorentz.
Yeah.
So it is
It is Minkowski. That's right.
Good. So 3D really is 2 plus 1.
Yeah, and here 2D is really 1 plus 1.
I see.
2D here is 1 plus 1, not 2
Thank
plus
you.
1.
Thank you.
All right. Another toy model, which I think I like to use as motivation, is 2D QCD. There, the gluon has no degrees of freedom. Okay? But at large n, it's tractable. In fact, de Tooft solved it. Okay? This taught us a lot about confinement. Okay. Another toy model is you can build Alice detector out of Legos. Right, this one probably doesn't have all the properties that you're interested in of the real one. So I'm going to look at 2 dimensions. I'm also going to take the limit of large central charge. Okay. So up until now, the central charge, I've allowed it to be anything. From now on, I'm going to take it to be large. So as I mentioned, the central charge is like the number of degrees of freedom. So this is like a classical limit. Okay, we're taking the limit where the number of degrees of freedom is large. In ADS3, this is related to Newton's constant by a very sharp relation. C is equal to 3 over 2g. This was actually first shown to us by Brown and Hinault over a decade before the discovery of ADS-CFT. So you can think of this as a semi-classical gravity limit. We're taking g Newton to be very small. Another way of thinking about it is, since I've fixed everything in units of the ADS radius, think of this as taking the Planck length to be very small compared to the ADS radius. So it gives us a huge region where sort of the curvature is tiny, and we can just look at Planck scale physics. Okay? So it looks a lot like theory in flat space. All right. So you may worry, taking G Newton to be very tiny, haven't I turned off all interesting gravity effects? Okay, well, we all know how to get large gravitational effects when gravity is very weak. You just take a gigantic mass. Okay? So we want to take G Newton to 0 with G Newton times the mass fixed. Okay? This is like the Schwarzschild radius is fixed. So what does this limit correspond to in the CFT? Okay. So G Newton is like 1 over the central charge. I told you dimensions are energies, or in this case masses. So taking their product fixed corresponds to taking dimension over C fixed. And by conformal symmetry, you can already see this is going to be something which gives interesting effects. Okay? So I mentioned if you take the operator product, something with itself, you find the energy momentum tensor. Okay? The OB coefficient of that is fixed by conformal invariance. We've chosen a specific normalization which is appropriate for the bootstrap. And in fact, you don't just get a single power of t, you actually find all powers of t with the same coefficient to the nth power.
Could you define your that sign, the half something
Subset.
circle? It's the
Subset.
mathematician.
Subset.
Yeah,
So
I just want to make sure it's the math definition.
this is not a set that's a subset of this. This is an abusive notation, which I like to use. It says that on the right-hand side you have a sum of many terms. Okay, one of these terms is the following.
Okay.
All right, so in the limit where delta over c is order 1, all of these guys contribute. Their OP coefficients are not small. We have to include them all. All right. And the energy momentum tensor in the CFT maps onto the graviton in ADS. So including all of these products of the energy momentum tensor in the CFT corresponds to resumming all multi-graviton contributions in ADS. Okay. So I'm going to show you how to do this. Since I'm interested in a bootstrap, I'll do it in the context of a 4-point function. So again, I'll focus on 4 operators. I'm going to look at the contribution from all of these powers of the energy momentum tensor. I want to calculate the contribution from all of them. You can think of this as dressing this contribution with powers of t mu, or in gravity, dressing it with multi-graviton contributions. The stressed contribution turns out to be the conformal block in 2 dimensions. Okay? Unlike in higher dimensions, right? What's special to 2 dimensions, among other things, is the conformal block includes all these. And that's related to the fact I mentioned the conformal group is actually infinitely large in 2 dimensions. Okay? Right? It actually has generators that relate all of these guys to each other. So all these terms that we need to include are actually controlled completely by symmetry. So in principle, they're known and computable. In practice, there's no closed form expression for them. Right? So we had to derive the closed form expression for our purposes. Right? I'll show you how to do this in the following limit, which I think of as a probe limit. Yes?
So to D, you lost what you just went through for D greater than equal to 3.
That's
the
correct.
Cluster
That's correct.
expansion.
That's right.
But you have something maybe even more powerful because.
Exactly.
Okay.
Good. So, all right, I'm going to look at the probe limit. So I mentioned I'm going to take dimension, in this case, dimension of rock operator over C fixed. I want to probe this with a little scissor operator, so I'll take its dimension to be very small. And I'll look at the 4-point function, 2 of these guys and 2 of these guys. All right, and in this limit, the total contribution of all these powers of this stress tensor will be computed and has a very simple effect. Right. Now I'll give you the basic idea for the argument. And it involves using coordinate transformations in a sort of subtle way. So part of the idea is a conformal transformation is a coordinate transformation. Right? When you do coordinate transformations, that changes the metric. Okay? Now, there's something known as the conformal anomaly, okay, which basically what it says is when you do this conformal transformation, T doesn't transform just the way you would naively guess. It also gets a vacuum expectation value. Okay? All right? So let's look at the 3-point function for phi rock t. Because of this conformal anomaly, we get this 1-point function in addition to what we would naively get. And the idea is we're going to choose our coordinate transformation precisely to make this term cancel against this term. Okay, so we'll completely absorb the contribution from a single stress tensor. Turns out this can always be done. Okay. Furthermore, in the limit of large central charge, turns out once you've canceled a single t, you've canceled off all t to the n contributions. Okay. So all of these contributions that we wanted to resum get completely absorbed by changing the metric from doing this coordinate transformation. Okay. So what this says is that the conformal blocks in 2 dimensions in this limit can be calculated. Okay. And in fact, the contribution from all these TDNs is exactly the same as the contribution with no t's, right, but in a different background metric. Okay. This is
The ground metric is still conformally the equivalent direction of one?
the new metric is conformally flat, but is not. It's not flat.
It's not conformal.
It is conformally flat, but it's not flat.
So this means that basically you apply the Rasora,
Yeah.
you get applying the Rasora can kill this stuff.
By applying a very special combination of the Rasora. So, but I'll show you the precise coordinate transformation on the next slide. All right. But this should surprise you because we've done all this in a theory with no gravity, or we've done it without making any reference to the gravitational theory. All right, so here's the coordinate transformation. It's very simple. You just take the old coordinates and you take them to some power. All right, the exponent is of the following form. Okay. So you can think of this as basically cutting out a wedge of space. Okay, so this is like creating a deficit angle. Okay. Now how does this relate to what happens in gravity? Okay. So here you should think about the analogy in gravity is you have, instead of some heavy operator, you have some, with a large dimension, you have some heavy point source for energy, which is very energetic. Okay, and it's known in 3-dimensional gravity ADS, there's a minimum threshold to make black holes. Okay, unlike in higher dimensions, okay, here in 3 dimensions, you can't have any black holes below 1 over hg Newton, okay, which in terms of CFT quantities means the dimension has to be greater than c over 12. Below this threshold, a local point mass in general relativity just makes a deficit angle singular. This deficit angle exactly matches what we got on the CFT side without reference to gravity. Things get more interesting if we look
Sorry,
at...
could you just go back for a minute?
Yeah.
That's the inequality. I'm not quite understanding the
Good.
inequality. So you have to have masses below this to get a black hole mass, and for...
It's the opposite. So if you... In flat space, there are no black holes.
Oh.
Right? So if you put in a point mass, what happens is you get a little deficit angle.
Mhm.
Okay, now as you increase the mass, the deficit angle gets bigger and bigger.
Mhm.
All right, until eventually you eat up 2 pi.
I
In the
see.
case where you're in ADS, when you eat up 2 pi, it's exactly at the point the horizon forms, and above that energy, you now have a black hole.
I see. Okay.
Below that, you just have a conical. So what all that happens below that is you just have this local little thing, which is just this little conical deficit.
Got it. Okay.
All right. So below this threshold, things match. Things get more interesting when we go above this threshold. Okay. On the CFT side, this means the dimension is greater than c over 12, and you can see something very interesting happens. This exponent becomes imaginary. Okay. We can define the imaginary part here to be the temperature of rock, okay, and I'll show you in the next 2 slides why that's the right definition. Okay. So how do we see that? The first thing we can look at is what is the 2-point function of this probe scissors operator in the background created by the state, okay, we call rock. And okay, you can work out the contribution from the vacuum plus all these TDNs by doing this coordinate transformation. And what you get is the following answer. It might not mean anything to you, but it in fact is known from work think in the 70s, that this is in fact exactly of the form of a thermal two-point function. Okay, so a two-point function of primary operators in a thermal background. Okay. However, notice we're not talking about a thermal background. We're talking about a pure state created by the rock operator. Okay. So we see that a pure state produces something that looks to low-dimension operators like a thermal background. This is related to what's known in statistical mechanics as eigenstate thermalization hypothesis. It says that in large classes of theories, okay, in the limit of large number of degrees of freedom, high energy eigenstates, when you probe them by macroscopic observables, they look to basically exponentially good accuracy, like they just create a thermal background. Okay. So you can see we're overturning centuries of conventional wisdom about rock, paper, scissors, which says that when rock and paper get together, paper should win, but actually rock has a temperature and just burns up paper. In fact, nothing beats rock. All right, what about, so that's how I was on the CFT side above this threshold. What about on the gravity side? So dimension is greater than is bound. All right, translated into ADS, that means the mass is greater than 1/18 Newton, which is this threshold for black holes. Okay. All right, so an object, okay, a point mass of this energy now does create a black hole in ADS, okay, as a horizon. As Hawking taught us, that means it has a temperature, right? The temperature exactly matches the expression for temperature we defined on the previous slide. Okay. That brings me to the end of the work that's been done that I want to talk to you about. Now I'll just say a couple words about future directions. So one thing we're trying to do is extend some of these 2D results to higher dimensions. Okay? So I showed you we got a lot of mileage out of the fact that there's this thing known as the conformal anomaly, which gives the energy momentum tensor vacuum expectation value that allowed us to cancel this and this. Well, you can say essentially all the same words in 4 and 6 dimensions as well. Okay? And you can do the same trick. Right? You can choose a new metric, which causes this and this to cancel.
So what about 3 and 5?
This does not work in 3 and 5 dimensions because there's no conformal anomaly.
Right.
Yeah, so it's hard to believe that it wouldn't be true in odd dimensions, but what it says is that the way of getting to whatever the final result is.
So if I wanted 4D quantum gravity, then I need 3D CFTs.
Yeah, they're 3D CFTs.
What
Yeah, but
plays
then
the role of z to the alpha?
Sorry?
What plays the role of z to the alpha?
No, so they're not exactly z to the alpha. So the way you define it is, in that case, is just as a Weyl rescaling. So just take g goes to g to e to the 2 sigma, and it's what is it? It's basically the metric ends up being so that the conformal factor ends up being x to some power, okay, which is, and the formula for alpha in terms of the dimension is slightly different in higher dimensions, okay? But you essentially get something which is, again, periodic, and the period satisfies this relation. So this type of scaling, which is exactly the scaling you would get when at a very large ADS black holes in Einstein gravity. Okay? So there's more work to do in terms of understanding what happens with higher powers of the energy momentum tensor, but this looks promising. The second direction I want to mention is going beyond the semi-classical limit. Right? So I talked to you about reproducing purely from the CFT side some of these facts about semi-classical gravity and ADS. But I think what becomes even more exciting is going beyond the semi-classical limit. Right? Looking at expansion in 1 over the central charge and matching quantum gravity effects. Or even better, learning about things which are non-perturbative in the central charge, which are non-perturbative effects in gravity. Here, there's another tool which I think is promising to try and put together with the bootstrap, okay, which is known as modular invariance. Just briefly, the idea is you can look at CFTs not in flat space but on a torus. Right? And you can think of the torus in 2 different ways. You can interchange the 2 cycles. Okay? Those are just 2 different descriptions of the same theory. Right? So the physics has to agree, but it agrees in a non-trivial way, which gives you information about the dimensions of operators. You can try and take that and put that into the bootstrap, in which case it becomes even more powerful because the only free parameters at that point are the OP coefficients. All right. So let me wrap up. So in summary, I think there's an enormous amount of information contained in the bootstrap equation. Okay. Showing you how to extract some of this. I think there's much more to be learned. A lot of this extraction relies on results on conformal blocks. Okay. In computation of them, I've shown you how to get some of these results, okay, on computations of conformal blocks. Talked a lot about the constraints of large central charge, which are very interesting. Another assumption I didn't say much about, but I think is also very interesting, is what happens if you assume that there are only a few operators in a theory with low dimensions. This also seems to have far-reaching conclusions. And then, lastly, talked about something that's an old dream, but I think it's a good dream, which is that ADS-3 gravity just may be simple enough to have tractable solutions. And I think one solution, which corresponds to gravitational theory with a nice low-energy limit, okay, I think one example of that form would teach us a huge amount about quantum gravity. So thanks very much.
Well, that seemed like it explained almost everything, but maybe there are still some questions.
Yeah.
So you're able to see this case where you had, in one way of looking at it, a pure state, another way, a thermal state.
Mm-hmm.
Can you, but then you presented that and then you run to the next thing. I mean, so how did you, which seemed like a pretty fantastically interesting result. I guess my own question is actually a request. Just what else would you say about that in this black hole information problem?
Good. So one thing is just going to higher orders, looking at quantum corrections, which should be contained in 1/c corrections, which are in principle contained in this block. Something that's more interesting is trying to actually learn about OP coefficients that relate to sort of the difference between different heavy states, okay, which would get to where in the CFT quantum black hole hair is contained. Okay, and I think trying to get information on that would be very interesting. Another thing is looking at the density of such states more precisely. Okay, this has to do with corrections to the entropy of black holes. Okay, so I view this as indeed sort of the starting point. Okay, the first term in an expansion, which is interesting to go beyond.
Other questions?
Yeah.
Maybe this one. Are there known CFT in 3D with large C? Because you mentioned.
Yeah. The hard part is not getting CFTs in 3D with large central charge. You can take your favorite CFT in 3 dimensions, take a large number of copies of it. Okay, you can even tie them together in a non-trivial way by taking orbifolds of them. Okay. The hard thing is getting this last thing. There are only a few light hours.
But is it clear if there is a continuum of theories of large C in 3 dimensions? Because they are not as many as
no one knows, but I would almost certainly guess there is not a continuum. But I would guess they become more closely spaced as you get to larger numbers.
So just to announce, we will have a discussion tomorrow from 1 to 2 in the Lagrange Lounge. So that will be another opportunity to pick Liam's brains. Okay, so let's thank Liam again.